Okay, so today we are going to talk about low power design. We'll start by talking about why do we need low power design, what are the motivations, and then what are the techniques that have been employed for doing low power design. In the last decade or so, power has become as critical in terms of a design optimization criteria as area and performance. Previously, the designs were primarily, when we talked of design, of course, one is to meet the functionality, but then in terms of what objectives optimizations you have to do to meet your objectives also revolved around either trying to reduce the area so that the cost gets reduced, or trying to reduce the or increase the performance so that you can meet the higher speed requirements of your application. But increasingly, apart from both area and performance, power has also become a very important component. And before we sort of talk about how it's become important, how do we meet the low power objectives, let's first see that why it has become important. The need for low power design originates from two different considerations. One which is very well, let's say, understood is in terms of mobile applications. There is increasingly a large number of applications where battery is to be used as a source of power, and you are not taking power from the main supply, but you are taking power from the battery. And as the battery technology do not change that drastically as electronics changes, so as you pack in more and more circuits into a smaller area and also pack in more and more circuits to give you higher performance, mobile computing applications, mobile transmission receiver applications, communication applications, all of them. So the battery life is a very critical factor in making a product commercially successful. You do not want, so because the cost of running the application is going to be dependent on what is the shelf life of the battery. So, and also even if you use rechargeable batteries, you still have to go back to the base station to be able to charge it very often. Essentially implies that your product is not going to be, is not customer friendly or not going to be popular if it consumes a lot of power. So that's a very important consideration for low power design. Another thing which is not that well understood is in terms of high frequency VLSI circuits. Forget the fact that the source of power is batteries, the source of power may be the main supply, but still, because you are now packing millions of transistors into a very small area, so we will just see that how it works. So the amount of heating that takes place is so large in a small area. So it actually compares, just to give an example, if you compare something like a heater which has a 20 centimeters diameter and it, let's say, consumes 1 kilowatt of power, roughly an area of pi r square around 300 centimeters square. So this is around slightly more than 3 watts per centimeter square. Whereas the dissipation is, if you consider a small IC chip which takes 5 watts and typical area is around 1.25 square centimeter, so it consumes 5 watts. So it's actually in terms of power consumption per unit area. So an IC chip, something like a processor, is much more, will become much hotter than even a heater which you use for heating applications. So that essentially means something which gets so hot is obviously there are problems of reliability, even the properties in terms of your conduction properties, that all that change considerably if a device becomes very hot, and it's also prone to failures. So even from this point of view, just from the point of view that power is dissipation is so high when you pack so many transistors in a small area, is critical for both circuit functionality and reliability. So one is talking of low power design not just from the point of view of mobile. Of course, mobile is very critical, but even from the point of view of high frequency VLSI design, low power is an important criteria. And what is the technology? Technology of choice is CMOS. Almost universally the technology of choice for low power is CMOS. Of course, people are working on other newer technologies, but today most commercially viable and successful technology is CMOS. And the reason also CMOS overtook other technologies like TTL and so on, which were faster, was primarily because CMOS has a much lower power consumption. And the reason it has a much lower power consumption is that the major power consumption component of power consumption is the switching power. Unlike in other technologies where you are, for example, like say in TTL, if a particular transistor is on, it is going to take some power because there is going to be, so you have the current flowing in on the collector through the collector resistance which forms the load, and that is going to dissipate power continuously. Whereas in case of CMOS that does not happen, so the power is consumed only when the transitions take place. So either at the rising edge, so each transition results in some power consumption, because which essentially results in the capacitor at the output getting charged or discharged, and that is going to take some power. So the switching power, of course there is some leakage and so on, so it is not that it is not there, but in most cases the leakages are substantially lower, and the only significant part of the power consumption is the switching power. So the transitions are the one which account for the switching power, which essentially implies that we can talk in terms of techniques which will be able to address this issue of fewer number of transitions. We can see that how we will do that. So the power dissipation for a gate in CMOS is given by this equation. It's a very well known and very used equation, and a lot of optimizations, power optimizations get done around it. So C load, so any gate which is driving it is driving a capacitance which is a load capacitance, and this load capacitance comes from number of sources. It comes from the input, so if there is a fan out, it is going to come from, if number of places this particular, if we have a gate, does not matter what gate, so it is going to some other gates, and each one of them is going to have a capacitance, and this transistor also has an output capacitance, and also this interconnect has a capacitance. So you have to basically, all of them are in parallel, they all add up, and that all corresponds to the load capacitance. So the larger the fan out, the larger the load capacitance that it is going to have. So that is one factor. VDD is the supply voltage, and it varies the square of the supply voltage. I will talk about this each transition in a moment. Let me talk divided by T cycle, 1 by T cycle for synchronous designs. This is nothing but the frequency of operation. So all changes are synchronized to the fastest frequency, which is, let us say, the master clock that you have in your system, and that is the frequency of operation. So you can write this equation as half C load into VDD square into F rather than into E. E is the expected number of transitions. So for example, in a particular clock cycle, if there is a transition that is going to occur, if you expect it to occur, then so whatever is the expectation of that. So that is a value between 0 and 1, and that gives you the total power consumption. So if this expectation is very few clock cycles when a transition is going to occur, then the power consumption will be lower, otherwise it will be high. So it directly depends upon the frequency, it depends upon square of the voltage, and depends upon directly upon the C load. So these are the three parameters, but unfortunately they are not independent, so you cannot sort of decrease one with the other, and we will see that there are some trade-offs that are possible, and they have they result in some changes. So what are the issues in low power design? So when we talk of low power design, the area of, and it's also, let me tell you, that's also a very current area of research. There are a lot of research that's going on. So people are interested in doing 4 different things. One is accurate estimations, because relatively a new field, still tools are getting developed for estimating the power that is consumed. And of course now there are fairly good tools available for estimating the power that is consumed at the lower levels of design. We will talk about what we mean by that. But one also is interested in estimating at a fairly high level of abstraction what is the power that is going to be consumed, because all the optimization that you will be working with a power budget, just like you work with the area budget, you work with performance requirements, you also work with a power budget. So you are interested in finding out what is going to be the power that is going to be consumed, and so that is one area of work that people are doing. So you try to model and estimate the power. Of course, we talk about a little bit more about power reducing design transformations. The other important thing is, of course, you know that this we can estimate it, but also we need to optimize it. So what are the circuit changes that I can do? What type of changes in the design I can do so that I can reduce the power that is consumed by the design for the same functionality and maybe even meeting the same performance? What is the these are the other two aspects which are related to slightly lower level of design. One is related to uniform distribution of power on the chip. Even though you said that okay, this is the power that this particular chip is going to consume, or let us say okay, this is typically rectangular. So is going to, so we don't want any hot spots on it. We don't want that most of the power, let us say some 50% of the power gets consumed in a small area within this, then it is going to get heated and it can even melt. Okay, so that is not really. So what is interested, what they do is they do a thermal profile on the chip. Once the chip is, so it is not just the power that is, you try to reduce the overall power, you also try to distribute the power so that the power gets more uniformly distributed. So you do a physical simulation after you have done the layout, after you have designed the chip in terms of the layout. Of course, this part is more related to how are you going to lay out the chip. So when you are doing the layout, see what is happening. Previously when people are doing the layout, they are only interested in area and performance. You try to pack components, there is one component like this, you try to pack all of them together closely so that you can reduce the total area. These corresponds to the various components you may have. And people are also interested in packing things closely because interconnects also take a delay and you are interested in reducing the interconnect. But now another factor that has come in is not that you can pack anything closely, because if you pack all these, let us say, are high power consuming modules, then you pack all of them closely, what will happen is this particular hotspot will get generated. So when you are doing a layout, again you need to bother about how the power is getting distributed, power consumption is getting distributed on the chip. So that is another type of. The fourth, which is more related to areas and material as well as areas related to packaging, which is not, which is related to how do we, agreed that we had to dissipate 3 watt, we have also distributed it, and as we saw that the power, actually the chip is going to become very hot, how are we going to cool this chip? So there is related to packaging, they talk of material which is thermally conducting but electrically insulating. There is a lot of work goes on materials like this which can take this power off, because actually a chip which is 1 centimeter actually gets packaged in a fairly large, almost 10 times the area or even more than that, in a package of that size. Okay, so this is mounted on it, and when it is mounted, it is mounted using the conducting material thermally, very highly conducting material, so that this heat can be taken off. There are cooling fins. There are also fans. People also put fans on top of it so that they can be cooled. So if you look into any of your PCs, so you will find that the processor chip definitely will have a very elaborate packaging, and most of the packaging is essentially for, of course there are a lot of pins, so I need to take the wires and take the interconnections, but today even more than the interconnections, the area is to be governed by what is the power that needs to be dissipated, because one needs to take the power off from the chip and put it onto the environment. So there is a lot of actually mechanical engineering that is required, and also material science that goes into trying to design good packaging, good conducting materials and so on for doing this. Of course, we will concentrate only on design. So primarily our intent in this course is to study design. So we will look at design, but before we talk of the design, I will give you a little bit of detail of estimation process. What is the type of power can be estimated by simulating the behavior at different levels. How do we, so once we simulate the behavior, I can count the transitions, and once I can count the transitions, so what I really need to do is to put a transition count at each of the nodes, and I can count the transition, or I can do some type of an accumulative, find the expected, what is the expected number of transitions, expected fraction of transitions, I can count that, and then I can do it, because things like C load, other things is statically can be computed. If you look at this, the equation VDD we know at what voltage we are operating the chip. C load I can do what is called an RC extraction of the circuit, where I try to extract the capacitance at each of the inputs, and I can find out what the capacitance value is there. Of course, here I need to know the complete layout, because I need to know the length of the interconnects and so on. I need to know the fan out at each point, and I can find the C load. So I can do that frequency of operation I know, so I know the T cycle for synchronous designs. So the only thing that is required to be estimated is dynamically that need to be estimated is E transitions, which is data dependent and which has to be done by simulations. So I can do that at different levels. At transistor level I can do it, at the gate level I can do it, at the RTL module level I can do it, and so these are at various different levels of abstraction. And the reason is that you go for a higher level of abstraction. Why do you go for a higher level of abstraction? Basically to reduce the size of your design, increase the speed of your estimation, because at each stage you get a factor of 5 to 10 in terms of the reduction in number of, from here to here you get around 5 to 10 reduction, from here to here you may get 10 to 50 reduction in terms of the number of components, so that your estimation process could be quick. Okay. So now if you are doing a gate level, you can use those equations to do this. If you are talking of an RTL module level, I had to build a model. See, please remember, whenever you go for a higher level of abstraction, just like we did in case of D algorithms and so on. So I had to build a model in terms of this. Let us say this is an ALU, and these are two inputs, and I need to build a model that how the power is consumed by this ALU, because now I am not going to each of the gates inside and modeling it, but I can model this ALU in terms of the power consumption on the input changes. And once I can model that, I can use this module library, these models, to estimate my power at this level. Accuracy typically will go down. As you go for higher and higher level of abstraction, the accuracy will go down, but the speed of estimation will go up, and primarily what you try to trade off is, without losing too much of accuracy, if you can increase substantial gain, substantial speeds, then the trade off is suitable. Then it's perhaps because you are doing a design exploration at the higher stage, you are actually using this, and then after you have selected a design, you may go down and do a gate level for one or two particular designs rather than all of them. There is another interesting thing that people are now trying to do is software power estimation. A lot of these designs now increasingly also contain a processor. So because the processor themselves have become very high speed, it's not that each time you try to build a specific IC for an application. You also use, typically a lot of solutions today contain a processor plus some hardware design. You do some hardware design for some part of your application which is very critical, for rest of it you use a processor. So when you try to do that, then you need to estimate the power that the software takes. So you have given a code, let us say an assembly code, maybe a C code which you have compiled and you have generated your assembly code, and can you estimate the power? So even without actually running this, can I estimate the power that the software, this particular software will take on the processor? The very interesting techniques have been evolved. Some of them are based on modeling at the instruction level. You can associate the power with each of the instruction. When an instruction gets executed, how much power it consumes, and then from there you try to estimate the power that the software takes. There are also techniques which have been developed at the architecture level. A lot of these things that I am talking about today is at the research level. So if it's also to give you a flavor of what's happening in this area. So at the architecture level, again there is an attempt to model at the architecture level, try to do the estimation for the power. So that was one problem, the estimation. Then the next problem, which is we are more interested in, is in talking about design transformations. So what one is interested in is take a design and generate another design by transforming this design. The second design meets all the other constraints, may have some area, may have some power constraint, performance constraints, but it also is lower in terms of the power. That is the type of. So there are many techniques that are employed. Some of them are sort of affect the others, so one has to be careful. So we will see a few of these techniques. Critical path reduction, reducing the number of operations, reducing the transition activity. Finally it is the transition activity that one is reducing. Either One reduces the C load or VDD or transition activity or frequency. One of the 4 parameters that come for computing the power we have to reduce. So, transition activity, reducing the interconnect capacitance, operation substitution, bit width optimization. So, these are all factors which are used for reducing the power. At the architectural level also there are certain things that are done which I have not put in over here because they are now very well understood. What we basically do is to what is called for any design, if the design is not to be continuously used, for example in mobile applications that is the case, you have a cell phone, you are not using the cell phone all the time. So, there is something called a sleep mode. Okay. The sleep mode is a mode in which basically a minimal part of the circuit is operational, but that part of the circuit is sufficient to initiate or trigger the start of the application. So, if a call comes, so basically only the logic which will generate bring the processor out of the sleep mode. So, there will be a special logic that will be designed which will generate the interrupt and whatever the required signals to bring the processor into operation. And of course, it has to be brought in within a certain period of time depending upon the requirement, but rest of it is frozen and there are no transitions that are taking place in rest of the circuit. Similarly, when you use a PC today, almost all PCs come with, once you are not typing in any, there is no activity on the keyboard for a significant period of time, the monitors are switched off and so on and so forth. So, many other things you go into a sleep mode and you do that. Okay, those are at the very high level architecture level. So, we are not talking of those transformations over here. Those have to be taken care of outside of the design itself. They are not really part of the design functionality of it. Those are the functionality that gets defined just to reduce the power. But that is also very critical because that is the time when the application is not active, then you reduce the power substantially. But let us talk about the critical path reduction and how does it help. If we are talking of the synchronous design, in a synchronous design it is a critical path which defines the frequency of operation. Okay. So, what this curve shows you is that reducing the critical path implies larger acceptable delays, which in turn means a lower VDD. If I can reduce my critical path, okay, because I have to have my clock. So, what happens is, see, if I am working with, what is the total performance? Performance is number of clocks into T clock, the time for the clock and the number of clocks. Okay. So, if I want to reduce the my T clock is going to be governed by what my critical path is. If I have 10 levels of logic in the critical path, let us say for a simple case, let us say all these 10 levels of logic is the same, then my delays that I am going to have is 10 gate delays for my clock cycle. My clock cycle should at least be corresponding to the 10 gate delays. But if I want to reduce, if I reduce the logic to 8 gates rather than 10 gates, if I have only 8 gates in my critical path, I reduce it to 2, then I can actually afford to, for the same T clock, I can afford to have a larger delay on each of the gates to meet the same time. So, I can afford to have a larger delay on each of the gates. And how can I have a larger delay? I can have a larger delay by as the VDD increases, the delay decreases. So, previously let us say I was operating here, and now because I can afford to have a larger delay, I can operate here. I can reduce my VDD to be able to accommodate a larger delay. And once I have a larger delay over here, the smaller VDD here, the power decreases by square of it. So, whatever. Of course, it is important to know that at which part of this curve you are operating, because there is a saturation effect. So, if you are operating at this level, the change is not going to bring you very much. Okay. So, but depending on at which level you are operating, so you can, for example, at this level again, the VDD that will reduce will be very small. So, depending upon which part of the curve that you are operating, you can reduce the VDD sometimes substantially, sometimes not by that much amount, and you can reduce the power that is consumed. So the critical path that you have in the circuit, so if you can flatten it and if you can reduce the number of levels, that will be important. The transition activity reduction, we are interested in reducing the transition activity, and there are many ways that one does this transition activity reduction. A very simple method is a reduction in variation in path lengths. Let me give you an example. Consider these two. Both of them achieve the same operation. What I am interested in doing is D is A plus B plus C plus D. I can implement it in this manner, I can implement it in this manner. If I implement it in this manner and monitor the activity over here, now it is all within the clock cycle. Okay, so of course, if you are, I am talking of now this is a combinational circuit, so even within the clock cycle you can see that what is the activity that happens over here. Now there will be some value that will be present here. At the beginning of the cycle, let us say we are talking of everything is happening within 2 clock cycles. Output, let us say, is registered. So if we start talking from the beginning of the clock cycle, when data here gets registered, data also gets registered in all these registers which store A, B, and C and D. But there will be some value that will be there, and that value will be added with D, and the output will come after a duration which is the delay of this. So some changes will take place here, and after some more time this D will reflect not just the addition of this and this, but addition of this and this plus this and this. So there will be some change that will occur over here, and after again some more time, of course before the next clock, if this data is to be latched in a register, I will get my final value which will be addition of A plus B plus C plus D. So what is happening over here is these, though of course I am only going to, in a synchronous design I am going to latch only the final value, but if you really look at it, there will be changes that will be occurring over here, 2 or 3 changes that will be occurring over here, depending upon the various paths that are present from the inputs to this output. So this number of this, when the number of paths are larger, then the number of changes that will happen at the output will be larger. Whereas if you look at this, what happens over here is, of course there will be some value present over here, because of that an output will come, but the next output will be the A, B plus C, C plus D, because these path lengths are more or less equal. So the changes that occur over here depends upon the variation in the path lengths, and so one of the techniques that is done is reduction in variation in path lengths. So the various, so if you consider any stage, so we are talking of from registers to registers, if you consider any stage of combination logic, you don't have too many variations in path lengths, and that will reduce the coding of numbers. It's a very interesting area where we try to, for the same set of computations, one tries to code the numbers in a certain manner so that the number of transitions decrease. It depends upon the nature of the data, the statistical, you can work at the statistical property of the data set that you are handling and so on. See, for example, if you look at the 2's complement arithmetic, and most of your computation, let us say, happens to be in a very small range around 0, most of your computation, then what's happening? Here let's say you are using 16-bit or 32-bit arithmetic, let's say you are using 32-bit arithmetic, but most of your numbers are in the range plus minus 256 or 255. Only the 8 bits, the last 8 bits are randomly changing depending upon the data. But rest of the 24 bits are going to be, but the data is changing around 0. There is a lot of variation around 0, let us say. Then all the other 24 bits are going to unnecessarily be changing from 0 to 1 each time in a 2's complement arithmetic, because the first data is whenever you change from here to here. So all the 32 bits will change, because in a 2's complement arithmetic that's how it works. So depending upon the range of data that you are typically operating on, the coding that you do of the numbers would also plays a major role in how many transitions that occur at the input. So for example, input to the registers, input to the ALUs, wherever this data is going, that's going to change substantially because each time when the data changes from. So maybe it may be better to work with sign magnitude representation in such a case. Is the number, because if your most of your data is in a very small dynamic range, which actually typically happens because the dynamic range of a number is chosen from more like worst case, like you want the data to grow up to a certain level, that's why you choose a large number of bits, but most of your data is not that large. So when that is going to happen, so it may be better because most of the 24 bits in a sign magnitude representation will be zeros. The MSB bits will be zeros, and there may not, it may not start any, create many transitions. Coding of states and instructions. Let's look at a state diagram. So when you look at Si to Sj, this is a transition. Let us say this transition happens very often. How do I code my states Si and Sj? From the power point of view, I should code it with a Hamming distance of 1. The distance, if the Hamming distance is small between the states which are transiting, then that is likely to generate fewer transitions, and is likely to, because the state register, so you have implementing a state register. So if you look at the input of your state register, so what do you get? So you go from the present state to the next state. This is what the state register does. Take the output, a Mealy model of a machine. This is your combinational logic. So if you are going from present state to next state, so the logic that generates this transitions is going to generate fewer transitions if I am coding them close to each other in terms of the binary coding. So it has also an influence on this. So this, of course, this is just one factor, but these are the factors. So when you coding of states and instructions. So similarly, when you talk of processor design, you can also code your instructions in such a manner that you generate fewer transitions. Because these instructions, if there is a certain sequence of instructions that are going to be executed, the number of bits that are going to change can all be decided by looking at how often these instructions are executed with each other. See, a lot of these things one can do when one knows the application. Okay, we are talking of designs which are more dedicated to one application or set of applications. Many of these things cannot be done in a very general design scenario because you don't know what is going to happen. But many of these, when you are taking a particular application and doing a design, you can do things like this. Coding of states and instructions could also play a role in it. Operation substitution. Some operations are very expensive in terms of power, and in case it can be replaced by equivalent operations, it is preferable. Multiply by, for example, a very key operation in most of the digital signal processing applications is the multiply operation. So you are doing multiplication, and if you look into the combinational circuit that does multiplication, the number of layers of combinational circuits, you are implementing it as a sequence of, when you are doing a combinational implementation, you are doing it as a set of adders, whatever the type of adders, either they are ripple carry adders or carry save adders and so on. But there are n stages of adders or n minus 1 stages of adders for doing an n by n multiplication. If you use a Booth's algorithm, if you use a sequential, again you require so many clock pulses to do the multiplication. So here you can talk in terms of not just the power, but the energy that is required to do the multiplication, because even if you replace it by a sequential, the power may be low, but the energy will be large because you are going to use that power for over a period of time, number of clock cycles to do the multiplication. Many times what happens is this multiplication is nothing but a multiplication of some number x with some constant c, which is very true in case of DSP, because excuse me, you are implementing equations like wi xi, a very common operation which is where you have some weights, whether you are doing a discrete cosine transform, the operations filtering and so on. So which very common operations where you are doing weighting the numbers and adding, first multiplying and then accumulating. So if I am going to do that, so if I take this multiplication and replace this by shift and add, and I don't have to have a shift and add stage for each one of them because I know this wi, I know the number of ones that are going to be present, so I need to perform only addition for those. And here there are very interesting ways of coding these weights in so that you actually reduce the number of ones. String of ones can be replaced by, so you can do some addition and subtraction just like you do in case of, for example, there is a string of ones, you can replace it by one addition and one subtraction and so on. So the number of ways that these weights can be coded, and you can also play around with trying to do some quantization effects. What you can do is, okay, you actually drop a few ones. What happens in terms of the performance of that? After all, these weights are finally, when you are generating these weights, they are anyway a discrete representation of some weights that you have got. So you are talking an additional domain, you have to have only few number of ones. So what you can do is you can play around and find out if I actually make some ones to zeros, what happens, whether the performance is acceptable. Sometimes you might have to add few more weights and so on. So there are a number of trade-offs that can be done, and finally to decide and replace a operation like multiply by shift and add, where you are doing only a few additions and not all the additions which a general multiplier will be requiring. So these are some of the type of changes. So for example, even architecturally, because we can change the frequency, let us say a situation you just need to compare performing one addition, I can actually use two adders. I want to replace this by this. Previously nobody will try to think of such a replacement, but when it comes to power, it actually can make sense, because what happens is, if let us say this is operating at a frequency of f, and if I can replace it and make it work at a frequency of f by 2. Now, what are the changes that, because I am working with a frequency of f by 2, I can also reduce my VDD. So there is going to be, VDD is going to be reduced in this cases. Of course, otherwise f by 2 would not have helped, because now I have to take the power for both the adders. So if I just make f to f by 2, I will not have had any advantage, because after all the equation that we considered was f into the expected probability. So if I do it for two adders and with half the frequency, I won't get any advantage, but I also get an advantage because I can reduce my VDD that the circuit works on, because my delays are lower now, and because of that I will get some advantage in terms of VDD square. So this actually circuit, one has to account for all the other inputs and output wiring and so on and so forth that takes place, but assuming that those are not substantial, there are situations when such a replacement would actually result in a lower power consumption. So something which one would never have done. So of course it may require a larger area than this, but if you are ready to trade off that larger area, that if you are ready to have a larger design, you might actually end up with a lower power in this case than in this case. So the power has completely changed the way the design is being done, because it has become a very important criteria. So type of things which optimizations which one needs to evolve are getting generated, which also address the issue of power. Okay. So that's where it is. Thank you.